Hello, today we're going to be looking at Chapter 10, starting with our very first hypothesis test. Chapter 10.1 is really all about understanding hypothesis testing and all the different pieces and parts, and then we'll move on to actually performing our own hypothesis tests in the rest of the chapter. So go ahead and grab your course packs and let's get ready to go. So 10.1, here we are. So we're going to do a little exploratory example here. So we are going to roll a six-sided die 12 times. You can either do a physical die or use an online dice simulator and count the number of fives that you roll. Okay, so you're going to go ahead and count yours. And I had 1. So that's after 12 times of rolling the dice, I got 1 5. Not so much luck today. But this is what the rest of our class had gotten. There were 2 people that got 0. There were 5 of us that got 1. 4 that got 2. 7 who got 3. We got some lucky people. And then 0, 0, 0, 0, 0. Very unlucky people. 0, 0, 0. And somebody reported getting 12 fives. That sounds interesting. So, what conclusions might you jump to from our results? This person down here is suspicious, right? So, we're not so sure if the student cheated or maybe just a fluke. Very lucky person that all 12 rolls were 5. Okay, so what kind of evidence do we have to support these conclusions? We have learned so far 2 methods of actually performing a hypothesis test that you don't even realize that we've been doing. So our classical method is using z-scores. And one way we've used the z-score so far, a typical way is if the value of outcome is more than 2 standard deviations above or below the mean, we consider that unusual. And we learned that back in chapter 3. And the other way that we discussed if something was unusual was using our p-value method, but we really didn't know that it was called the p-value method. We did know that it was called probability, right? So we said, if the probability of the fluke actually happening is less than 0.05, right, which is 5%, then we say that that is unusual. So we are going to transform these 2 typical ways of saying something's unusual into more specific pointed methods. It might not be 2 standard deviations now. We might say it's more like 1.2 standard deviations or 2.3 standard deviations, right? Or you might say 1% instead of 5%. But these are going to be our typical methods. For the most part, the rest of our semester, we're going to use the p-value method because most computer software that's what they're using. So it says, is it possible for a person to have a die with no 5s on it? It's possible, right? But not likely. So this was, so we want to know, is it possible for a dice to have no 5s? Is it possible for a dice to have all 5s? That's totally possible, right? If our dice had all 5s, and that's how our one person rolled 12 5s, because it's not going to be likely that our 6-sided dice would be rolled and get 12 times and get all of them to be a 5. That's almost impossible. So let's turn to page 222 here. So 222 talks about our first step in hypothesis testing. So first we have to have a hypothesis, a statement regarding a characteristic of one or more populations. And hypothesis testing is a formal process based on sample evidence and probability used to test hypotheses. A couple steps here are making a statement regarding the nature of the population. We're going to then collect some evidence or data, and then we're going to analyze the plausibility of our evidence in our statement. So in this chapter, we will assume that the population parameters are certain values, and then we are going to test whether they make sense in light of known sample statistics. Okay, so step one is we assume that rolling a 5 would be 1 in 6. And then the data that we collected was we rolled 12 times, and student A, we'll call them, they actually got 12 out of 12. They got 5s. And so what we want to do is analyze assess the plausibility of the statement. So what is the probability of getting when n equals 12 and the probability is 1/6, actually getting all 12? That's what we want to know. That's what we're going to prove. And we're going to look into that. So some things we have to recall back from chapters 1 and 3 is if we're talking about a population of data, it's all of the individuals, and that characteristic is going to be a parameter. It's usually unknown because it's doubtful that we're going to have all of the data, and that variability is pretty constant. Now, if we have sample data, that's a subset of our population. That characteristic is called a statistic, and this value is usually known because we actually have sample data, and the variability depends on the sample. Okay, so there are 4 main parameters that we have of interest that we might look at. One would be the population mean. One would be the population proportion. One would be the standard deviation. And the other one would be the variance. But we are only going to look at these 2 this semester. Okay. So let's move on to page 213. Hypothesis testing step 1. So hypothesis testing step 1, making hypotheses. The null hypothesis, that's labeled H0, is a statement of no change, no effect, or no difference in the population parameter of interest. This statement is assumed to be true until evidence indicates otherwise. Okay, so this is what we think is true about the population. The alternative hypothesis, we call that H1 or HA. It's a statement that claims there is some change. Sometimes it's more we're proving, or less, or different in the population parameter. A few notes here. A hypothesis test is like a trial. We start by assuming the null hypothesis is true. If the data provides strong enough evidence against the null hypothesis, we will reject it and believe the alternative hypothesis may be true. Some potential parameters for hypotheses would be the mu, which is the mean, or the population proportion, or the standard deviation, or variance. But as I mentioned before, we're only focusing on the mean and proportion this semester. So there's 3 types of tests that we could run, and one we call them left-tailed or right-tailed or two-tailed, but the left-tailed and right-tailed are going to just be called one-tailed tests. So if we're talking about a right-tailed test, it's going to be a greater than, and some key words are going to be greater than, more, some other words that we're going to look for are larger, bigger. And so you'll notice that the H sub 0, the null hypothesis, is always has an equal to, and the H1 will then have the inequality. So this is a greater than. So we could have something like this, where we're talking about the mean is equal to 2, or we might say the mean is greater than 2. Okay, so the HO always has the equal. A left-tailed test is going to have words that would indicate something like less than, fewer, smaller than, and it's going to have this less than symbol, okay? And an example here might be, this time we're going to use it using the population proportion. So it might be P is equal to 0.2, and H1 is going to be P is less than 0.2. So we always have some value that we think is true about the population, and that's going to be always here, some value. Notice the value always stays the same, and the symbol always stays the same for the parameter. It's the H1's greater than, less than, or in the last case, and not equal to. So in this case, a two-tailed test, we're going to see words something like different, not equal to, other than. You might also hear them say or read words that say, indicate changed from, something like that. So an example like this might be, the mu is equal to 3.1, or the mu is not equal to 3.1. So these are the three types of tests: a right-tailed, a left-tailed, and a two-tailed. Or in other words, a greater than, a less than, and a not equal to. So example 1 gives you 3 scenarios that we're going to go through, and it's asking us to state the type of test and write the null and alternative hypotheses in symbols. So it says, active management of labor is a group of interventions designed to help reduce the length of labor and the rate of cesarean deliveries of babies. According to a recent article, the average cost of having a baby in a U.S. hospital is $2,528. A random sample of 200 AML deliveries had a mean cost of $2,480 with a standard deviation of 766. Do the data provide sufficient evidence to conclude that, on average, AML reduces the cost of having a baby in a U.S. hospital? Okay, so we're looking for 3 things actually here. We're looking for the parameter. So what parameter are we talking about here? Is it the mean? Is it the proportion, or is it the standard deviation? And we're looking for the sum value from the population that we're discussing, and we're looking for the type. And the type could be greater than, less than, or not equal to. Okay, so the parameter, so for if it's talking about mean or proportion or standard deviation. So let's look at the question that usually gets us, if we look for the question at the end, it usually will tell us most of what we need to know. Do the data provide sufficient evidence to conclude that on average reduces the cost? So that must be, they're talking about the population mean, because they're talking about it up here as well as the average cost. Okay, on average. Okay, so it's going to be HO and H1, and it's going to be the mean. And HO is always an equal to. And we want to know what they think is true about this, the population. Well, they gave us 2 means, 2,528, and then they also said a random sample, and they had an average mean cost of $24.80. Well, I can tell you right now, as soon as they start talking about a sample, that's their evidence. And we're not going to deal with that until steps 3, 4, and 5 in the hypothesis test. So you can automatically take the random sample and just delete that right here because that is just evidence. We don't need that yet. So we're talking about the 25, 28, 25, 28. And it says reduces. They believe that it reduces the cost. So that is going to be a less than. Second example says, according to the National Household Survey on Drug Abuse, 13.6% of 18 to 25-year-olds in the U.S. were current users of marijuana or hashish. In 2000, a psychology researcher at a university believes that the proportion of 18 to 25-year-olds who are current users of those drugs has changed from the 2000 percentage. They conduct a poll and 1,283 random people in the US in that age group and find that 205 of them currently use those drugs. Do the data provide sufficient evidence to support the researcher's claim? Okay, well, as soon as they start talking about a poll, that's sample data, and we don't need that yet until steps 3, 4, and 5. So we can automatically get rid of that. Let's see, what are they talking about? Are they talking about means, proportions, standard deviations, or variance? And because they're talking about a percentage, we know that it's going to be P. So this is going to be P. And this is what they think is true back in 2000, year 2000, so 13.6. So we're going to write it as 0.136. And then it says a psychology researcher at a university believes that the proportions who are current users of those drugs has changed. So change means that it's a not equal to 0.136. The third example here says a fast food restaurant chain states that the standard deviation of the wait times for customers in the drive-through line is 3 minutes. A consumer's rights agency thinks the variability in wait times is more than this. They obtained a random sample of 27 drive-through wait times and find a standard deviation of 3.9 minutes. Okay, so the business about this sample, we don't even have to worry about yet. Okay. What are we talking about? It says that they're talking about standard deviation. So even though we're not going to really do any tests with this in this semester, this is one of the possibilities. So we're going to just use it to practice writing our hypothesis test. So standard deviation, and they think the standard deviation is 3 minutes. And a consumer's rights agency thinks so variability in wait times is more than 3. Okay. So 3 good examples here. So let's move on to page 225. Hypothesis testing. Making decisions and writing conclusions. So we just learned about step 1. Now we're going to learn about steps 5 and 6. And then later on, we'll talk about steps 2, 3, and 4 in the middle. So steps 5 and 6 are our conclusions and how we write them. So step 5 is all about our decision, and then our conclusion that we're going to write up is step 6. So for step 5, our decision dictates what our conclusion is going to be. So we have 2 possible decisions we could come up with. One decision might be to reject the null hypothesis. That means reject H0. This is one. And if we reject the null hypothesis, we're actually going to write it like this. There is sufficient evidence to support the claim that, and then we're going to fill in the blank with whatever H1 is. Because if we're rejecting H0, we now think H1 is true. The second way we could make a decision is we could say we do not reject the null hypothesis. So we would write it as do not reject H0. And if we don't reject H0, that means we can't support H1 because you can only agree with one of them, H0 or H1. So there is not sufficient evidence to support the claim that, and then we're going to fill in H1 in words. This is kind of tricky. There's only two choices, either reject H0 or do not reject H0. Notice we never accept or prove. We just say that we have sufficient evidence to support or we do not have sufficient evidence support. So let's look at our example 2 here. It says boxes of a certain kind of cereal are labeled as containing 16 ounces. An inspector thinks that the mean weight may be less than this so that company can scam its customers. He collects a random sample of cereal boxes and weighs them to test his data. State the null and alternative hypotheses and symbols. So 16 ounces, because there's units, we know it must be mean weight. Yep, so mean is 16. And they think it's going to be less than, so less than 16. So what if the inspector decides to reject the null hypothesis? How would a statistician write the conclusion? So if we're rejecting the null hypothesis, we're going to write it like this. There is sufficient evidence. So there is sufficient evidence to support the claim that, and we're going to fill in the H1, which is right here, that the mean weight is less than 16 ounces. If the inspector decides to not reject the null hypothesis, how would a statistician write the conclusion? So we would then write, there is not, so we're following this method up here, there is not sufficient evidence to support the claim. There is not sufficient evidence. Support the claim that, and then we're going to just fill in the same thing, the mean weight is less than 16 ounces. So you're always filling in the description for for H1, but you're either saying yes, there is sufficient evidence to support, or you're saying no, there is not sufficient evidence to support. And a little note here is, it's weird how we write this as statistician, because step 5 talks all about the H0, right, about the null hypothesis. And step 6 refers to everything about the H1. And so it's kind of weird how, and they're opposite of each other. So just be very cautious. This deserves a major sticky note for your note sheet to kind of refer back to. 226. So page 226, we have a little table here of our 4 possible outcomes and hypothesis testing. And it says 4 possible outcomes. So we have H0 is true, or H1 is false. And here H0 is false, or H1 is so if H0 is true, H1 is false. If H0 is false, then H1 is true. Okay. So if H0 is true and we don't reject H0, that's a correct decision, true and true. If H0 is true, but they reject H0, That's called a type 1 error. And we define that with our alpha symbol. Now, if H0 is false, then, and they don't reject it, that's a type 2 error, and we give that a beta symbol here. And if H0 is false and they reject it, that's a good statement. So we're going to put this with a story to it so it'll make a little bit more sense. So if we go to the criminal justice system, we are going to state the null and hypothesis of a scenario. And the null could be person is innocent. So they did not commit crime. And H1 is they did commit crime. So it says describe the types of possible outcomes in the grid below. Okay, so we already did that here. We said did not commit, did commit. So the actual situation. So H0 is true. H0 is true. So did not commit. And the decision they made was they do not reject H0. So that means they said they were innocent. And so they did not commit the crime and they said they were innocent. So this is a correct decision. That's good. Let's say they did not actually commit the crime, but they charged them guilty. The jury said they were guilty even though they did not commit the crime. This is a type 1 error. This is a very bad situation. Now let's look at the other possibility of H0 is false. So they did commit the crime here. So let's say they did commit the crime, but the jury said they were innocent. That's not good either, right? They actually committed the crime, but the jury said they're innocent and they go free, even though they were guilty. So not good, not good. So this is bad. This is a type 2 error. Beta. And they did commit the crime, but they were also found guilty. So that's good. They did commit the crime and the jury agreed that they were guilty. So this is a correct decision. Those are both. So these are both good. This is a type 1. So type 1 error that we're going to really focus on this semester is here. When H0 is true, but they rejected H0. We don't really want, we're trying to prevent that from happening. So let's look at example 4 here. Example 4 says, determine whether the outcome is a type 1 error, a type 2 error, or the correct decision. So it says, a test is made of H0, the sigma is equal to 0.5, versus H1 is it's greater than 0.5. So the true value is 0.6. So we're going to ask, is the true value agree with H0 or H1? So the true value actually agrees with H1, right? So, and H0 is rejected. So let's go to our table. So our table says it agreed with H1, so H1, and it was rejected. So that's a correct decision, right? It agreed with H1 and it was rejected, so that's a correct decision. test 2, or B, says a test is made and the mean is equal to 54 versus H1, the mean is not equal to 54. The true value is 454. Oh, sorry, 454. So it does agree with H0, and H0 is rejected. So it says we agree with H0. H0 is true, but H0 is rejected. So H0 is true, but H0 is rejected. That's a type 1 error. And then we have C, a test is made for HO and P is equal to 20% versus P is less than 20%. The true value of P is 0.17 and H0 is not rejected. 0.17. So it's actually, H0 is actually not true, right? Because P is actually less than 20% and H0 is not rejected. So H0 is actually false because H1 is true. H1 is true, but H0 is not rejected. So do not reject, but H1 is false. So this is a type 2 error. Yikes. So type 1 error, rate is the alpha. It's a probability of a type 1 error, which is also the probability of rejecting H0 when H0 is true. The symbol is alpha. We've already talked about that. We also call this our level of significance. We introduced this symbol back in chapter 7 when we were finding probabilities under the curve. And the alpha is going to be given for every problem. The type 2 error rate is called the beta. And this is the probability of not rejecting H0 when H0 is false. So beta is much more difficult to calculate and work with than alpha, so it's not calculated in this course. This is the only time we're really going to be bringing it up. And if we talk about the power of a test, that's 1 minus beta. The probability of rejecting a null hypothesis when the alternative hypothesis is true. So the probability of not rejecting H0. Okay, so it says, what is the relationship between alpha and beta? So there's some give and take. Meaning, to some extent, when alpha goes up, beta goes down, but not equally. Okay. So let's look at a little example. And like I said, we're only talking about alpha this semester, so don't get too worried about understanding beta. Example 5 says, Charlie will perform a hypothesis test at alpha equal to 0.05, level of significance. Felice will perform the same test at the alpha 0.01 level of significance. If H0 is true, who has the greater probability of making a type 1 error? Okay, so remember, alpha by definition is the probability of making a type 1 error right there. It says it probability of making a type 1 error. So whoever has the bigger alpha, which is Charlie. The alpha is bigger. And alpha by definition is the probability of a type 1 error. So if H0 is false, who has a greater probability of making a type 2 error? And that would be Felice, because the alpha is smaller. And like I said, we only have to understand that alpha is a probability of making a type 1 error. That's all we have to really worry about. Let's go ahead and flip to the last page of 2.1 on page 228. And we are going to talk about applications of type 1 and type 2 errors. So by far the most important application of type 1 and type 2 errors is in screening tests. So we have all sorts of screening tests that we use. One is security screening, metal detectors, stadiums, amusement parks. Sometimes they use it in inventory control, automated inventory control system, Computers, they use it for computer security, malware detection, spam filtering, optional optical character recognition, biometrics, and also in medicine. So they use it for screening for mammograms, x-rays, colonoscopy, COVID-19, blood pressure, right? We've heard a lot with COVID-19 about it's a false positive or it's a false negative, right? And so that's what we're going to talk about here with this medical screening. So we're going to do an example with medical screening here that says, assume H0 is person does not have the disease or the trait. Fill out the contingency table for the COVID-19 testing. Label the errors as either false positive or false negative. So true is does not have COVID and disease not detected from the actual test. And then over here is does have COVID. And then if this one is the disease is not detected, this one is the disease is detected. Disease is detected. And this is the decision means it's by the test. So the medical test. Screening test. Okay. So H0 is does not have COVID, and H1 is does have COVID. Okay, so let's look at our possible outcomes. So this is they do not actually have COVID and the disease is not detected. So this is what we're going to call down below specificity. It is the confidence of the test, 1 minus alpha. It's the probability of correctly not rejecting a true null hypothesis. In screening tests, it measures the proportion of actual negatives which are correctly classified as such. Okay, so this is the specificity. So this is a correct decision, right? And this is called specificity. Specificity. Okay. So let's look at the next one. Let's say they do not have COVID, but the screening test says that there is disease detected. Okay, so this is a false positive. And this is called their alpha. Okay. And to fill in down here, it says, what are the consequences of this type 1 error? This is the type 1 error, right? Type 1 error. So they really don't have it, but disease is detected. So type 1 error for COVID, it could be given medicine unnecessarily. Medication unnecessarily. They're having to quarantine, but maybe they don't need to, right? If they really are not sick. And then over here, they do actually have COVID, but the disease was not detected. That's not good either, is it? That's beta. And that's a type 2 error. Yep, that's not good. And then that, you know, what could be an issue with that is they could be spreading the disease, right, to others, because if they don't think they have it and they're out and about, they're giving off those spores of the disease, and they could be infecting other people. And then over here, they do have COVID and the disease is detected, and that's a good, correct outcome, and that's called sensitivity. And that's the power of the test, is the probability of correctly rejecting a false null hypothesis. In screening tests, it measures the proportion of actual positives which are correctly classified as such. Okay, so these two are opposites and these two are opposites as far as 1 minus sensitivity. Okay. And that is all for lesson 10.1, and we will see you back for 10.2.